Hi, my name's Sunny.
And I'm Ray.
And I'm Crystal. We're here to show you how to use solar energy in your home. You'll see how to keep your house warm in the winter.
And cool in the summer.
Using just sunlight for fuel. Not only that, we'll find out how to turn sunlight into electricity.
And how to heat water with solar energy.
And cook food with the sun. Usually we do these things by burning fossil fuels, such as coal and natural gas.
But fossil fuels are running out, and burning them is hurting the environment.
The sun, however, is a non-polluting source of energy that should last for at least another couple million years. You know, solar power is nothing new. People have been using it for centuries. Let's take a look at the first people to use the sun to heat their homes.
Native Americans in Colorado were some of the first people in history to use the principles of solar design. Over 1,000 years ago, they built a settlement in a south-facing cliff. The early Greeks built entire cities where every home could face south to take advantage of the winter sun's heat. And the ancient Romans improved on the Greek designs and developed glass, which let sunlight in without letting heat out. In the 18th century, the Dutch grew exotic plants in south-facing glass greenhouses that captured wintertime solar heat.
So why did all these people face their buildings to the south?
And how would that help them stay warm in the winter?
To answer, let's look at the Earth in space. The Earth rotates on its north-south axis. This axis is not perpendicular to the sun's rays, however. It's tilted 23.5 degrees. During the summer, the northern hemisphere is tilted toward the sun and receives more light and heat. As the Earth orbits the sun, the northern hemisphere tilts away and winter sets in. Viewed from the Earth's surface, the sun's position in the sky changes throughout the year. The sun rises in the east and arcs across the sky, reaching its highest point at noon. During winter in the northern hemisphere, the sun's arc is much lower in the southern sky.
So that's why they face their buildings towards the south, to get as much sunlight as possible during the winter.
But to heat a house with sunlight efficiently, we first need to understand exactly what heat is and how it is transferred from one object to another. Heat is a form of energy, the energy of atoms in motion. And that energy flows from one object to another in 3 ways, through radiation, convection, and conduction.
Radiation is the direct transfer of heat by electromagnetic waves. Conduction is the movement of heat through a solid substance. Convection is the transfer of heat through fluids, or between any surface and a fluid.
We'll take turns explaining these 3 different forms of heat transfer.
Ray and I will start with radiation. And I'll be back later to show you how conduction works. See ya!
First, let's look at what happens to the atoms in an object when it's heated up.
All matter is composed of vibrating atoms. The hotter an object is, the faster these atoms vibrate. When an object warms up, it gives off heat waves.
Okay. Heat causes atoms to vibrate faster.
Yeah, that's right. And now let's see how radiation works.
The sun produces a wide spectrum of electromagnetic radiation, including visible light, ultraviolet light, and infrared light, also called heat. This light acts both like waves and like particles. When light shines on an object, some heat is absorbed into the object and some bounces off, depending upon how reflective the surface is. This is the process of heat transfer by radiation. Black surfaces absorb almost all of the light and heat that falls on them. White surfaces reflect light and heat much more efficiently. The amount of heat absorbed by an object also depends on the angle at which the heat waves strike it. The greatest amount of energy is absorbed when heat waves strike an object at a perpendicular or 90-degree right angle. The more oblique or slanted the angle is, the more energy is reflected from the surface.
Radiation is only one way that heat is transferred. It's also done through a process called conduction. When one end of a metal rod is held in a flame, the other end gets hot too. Let's see what's happening to the metal at an atomic level.
As the atoms heat up, their vibrational energy is passed on to the neighboring atoms. This is the process of heat transfer by conduction.
Many materials, such as leather and wood, are poor conductors and transfer heat slowly. Poor conductors are also called insulators. That's why I can pick up this hot metal bar with these leather gloves and hold it for a little while before it gets too hot.
If it's not moving, water is a crummy conductor. But if currents can form in water, it can transfer heat very well.
This process of heat transfer is called convection. Take a look.
As the water at the bottom heats up, it rises. Cold water from the sides flows into the space left by the rising hot water, and a circulation loop forms. The water is flowing in a loop called a convection current.
When any cold fluid moves across the surface of a warm substance, heat is transferred to the cold fluid.
Even though air is not wet, it acts like the fluid too.
That's why blowing air across the surface of this water cools it down.
The faster the air is moving, the more heat it carries away. On the other hand, if we can stop air from moving at all, it transfers heat very slowly and acts as an insulator.
That's why this down vest is so warm. The down stuffing has thousands of tiny spaces that trap air and keep it from moving.
And the trapped air acts as an insulator. The thicker the layer of trapped air, the harder it is for heat to escape.
That's why you stuff insulation into the walls of buildings, to trap air and keep heat from moving through the walls.
And if we use windows with 2 panes of glass and an airspace in between, even though windows can act like insulators. Let's see how all this works in a house.
When sunlight enters the window, it heats up the room. Once warm, the room itself begins to radiate heat waves. Some of these heat waves are reflected back from the glass. Sunlight passes through the glass into the room more easily than heat waves pass out. The insulation in the ceiling and walls makes it harder for the heat to escape from the building. The thicker the insulation is, the more time it takes for the building to cool down.
But even with insulation, the house still loses heat. And after a few hours of darkness, it gets cold again.
And there are a lot of cloudy days in the winter, when there isn't even enough sunshine to heat the house.
We need a way to store the heat from the sunny days to keep the house warm when it's cloudy or dark.
Have you noticed that after a hot day, that boulder stays warm at night? That's because it has a large amount of thermal mass. Thermal mass is the ability of a material to absorb and store heat. Dense materials like stone or water have high thermal mass. The ideal house has plenty of thermal mass to store heat. Walls and floors of concrete or stone are good examples of thermal mass. They can heat up during the day and release that heat into the room during the night.
With that big window facing south, wouldn't the house get pretty hot on a sunny day?
It could, and the sun can cause a lot of glare inside.
Well, I wonder what would happen if we put the concrete wall right behind the window.
Great idea. A guy named Trom already tried it.
This thermal mass wall captures daytime solar heat. If that heat is needed during the day, vents can be opened at the top and bottom of the wall, allowing convection currents to flow. As air between the wall and the window heats up, it rises and passes into the room, to be replaced by cooler air near the floor. The heat of the sun works its way slowly through the stone wall by conduction and begins to radiate into the room at night. This type of thermal mass wall is called a Trom wall. Trom walls can be made of many different materials, including water. Water has a greater heat storage capacity than either concrete or stone. If vents are installed on the outside of the building, tram walls can keep houses cooler in the summer also. Rising hot air is vented to the outside, drawing cooler air from the north side of the house into the living space. The wall then acts as a natural convection cooler. To allow more sunlight into the building, larger windows can be built into the tram wall. Windows can also be placed above the wall. These higher windows allow sunlight to reach deeper into the room and are called clerestory windows. Using the sun to light the house and saving the energy used by electric lights is a process known as daylighting. It's important that the roof overhang shade the wall from the summer sun, yet still let the lower winter sun shine on it.
Hey, Sunny, what are you doing?
Hi, Crystal. I was just wondering if we could use the sun to heat water instead of using this gas-powered water heater.
Oh, sure we can. You know how a regular hot water heater works, right?
Well, it's just a big tank of water with a gas burner at the bottom. Cold water comes in one pipe, hot water goes out the other pipe, and goes to all the hot water faucets in the house.
Right. Well, one of the simplest ways to heat water with sunlight is to take another tank like this, paint it black to absorb heat better, and then put it outside in the sun to get warm.
I don't know about you, Crystal, but I feel another history lesson coming on.
Some of the first solar water heaters were developed in the 19th century. These simple batch heaters took all day for the water to get hot, even in the middle of summer.
People did not want to wait all day for hot water. So to heat water more quickly, people started using several black tubes instead of just one black tank. They put these tubes inside an insulated box with a glass top, like this. This is a solar collector. The solar collector is really just a tiny room with the water acting as the thermal mass. Here's how it works.
There are many types of solar collectors and several ways to connect them to household water systems. Cold water enters this collector at the bottom, is warmed by the sun, and rises to the top. In mild climates, where freezing is not a problem, solar collectors can be attached in series with regular hot water heaters. A regular water heater uses gas or electricity to heat a tank of water. When a hot water faucet is opened, cold water flows into the bottom of the tank and pushes hot water out the top. To heat water with sunlight, the cold water pipe is attached to the bottom of the solar collector. The hot water from the top of the collector can then be piped into the cold water inlet on the standard water heater. Now, when hot water is drawn out of the water heater, it's replaced by preheated water from the solar collector.
Wow, that's cool. The solar water heater outside warms the water before it comes to this water heater.
Yeah, but it still wastes energy to use this kind of water heater.
Why?
Because we're keeping this big tank of water hot all the time, just so it'll be ready when we need it.
Sort of like keeping your car running all the time, just in case you need to drive somewhere. Is there a way to heat water only when you need it?
Yeah, there is, by using a tankless water heater. Look.
Instead of a big tank of water, gas-fired tankless water heaters use a metal coil called a heat exchanger. When a hot water faucet opens, a gas burner ignites and rapidly heats the water as it flows through the coil. This system can be up to 4 times more efficient than a standard gas water heater, and some models can use preheated water from solar collectors.
This is a solar oven. These aluminum panels reflect sunlight into this box. It can get up to 400 degrees inside. That's plenty hot enough to bake cookies. Cookies are done.
Wow, those look great. Thanks, Ray.
There's one more really shocking thing we can do with sunlight. Turn it into electricity. This is a photovoltaic module, also known as a solar panel. When light shines on it, an electrical current is produced. A little history, please.
The photovoltaic effect was discovered in 1876, but it wasn't until 1953 that Bell Laboratories made solar cells that were powerful enough to run everyday electrical equipment.
Photovoltaic modules have no moving parts and run silently without polluting the environment. Let's see how they work.
In addition to behaving as waves, sunlight also operates as individual packets of energy called photons. Photovoltaic modules consist of many solar cells. These cells are made of materials like silicon, one of the most common elements on Earth. The individual cell is designed with a positive and a negative layer to create an electric field just like in a battery. As photons are absorbed in the cell, their energy causes electrons to become free. The electrons move through the connecting wire. This flow of electrons is what we call electricity. Individual solar cells produce a very small amount of electricity, typically 1/2 of 1 volt, by wiring cells in series connecting the negative wire of one cell to the positive wire of the next. The voltage of the cells is added together. These large groups of cells are known as photovoltaic modules. There are different types of photovoltaic modules. This flexible one is glued onto a standard metal roofing panel, so the roof itself is the solar array. By combining solar cells in photovoltaic modules, we can produce just the right amount of electricity to perform a specific job, no matter how large or small.
You get the most energy out of a module when light hits it at a right angle. We've attached this module to a water pump.
If you tilt it away from the sun, the pump slows down. Bring it back to the right angle, the pump speeds up.
And even a little bit of shade can turn the pump off completely.
If we want to use photovoltaics to power our houses, there's something else we need to know. The type of electricity from solar panels is not the type of electricity used to run the devices in our homes.
Wait, there are 2 different types of electricity?
Yep, DC electricity and AC electricity.
Photovoltaic modules produce direct current, or DC electricity. DC electricity flows in only one direction from the modules through the electrical load. The utility grid, through power lines, brings a different kind of electricity to your home, alternating current, or AC electricity. This electricity flows through a meter to all the electrical outlets in the walls. AC electricity, or alternating current, flows through the wires in one direction and then changes direction and flows the other way. The direction of current flow alternates 60 times a second.
All the stuff in your house runs on AC electricity. To use the DC electricity for solar panels, you have to turn it to AC electricity. To do this, we need a device called an inverter.
Wait a second, Sonny. You mean this little box turns the DC electricity from the solar panels into the same kind of electricity we get from the telephone poles?
That's right, Ray. And if you get a really good inverter, you can even send electricity from your solar panels back into the meter to the utility grid.
So the meter turns backward?
That's right, Ray.
So what do you call that when you run electricity from the solar panel into an inverter back into the utility grid?
It's called a utility intertie system.
During the day, the photovoltaic modules pump electricity through the inverter into the utility grid, and the electric meter turns backwards. At night, or when using more electricity than the photovoltaics produce, electricity flows from the utility grid and the meter turns forward. This type of system is called a utility intertie system.
Wow, we've done a lot with solar power. We've heated and cooled our house.
We've heated our water and cooked our food.
We've even made electricity from the sun. But there's still one piece of solar technology that would save us a whole lot of fossil fuels. It's not a new technology, but it works just as good as ever. It's a tensile textile dehydration device, also known as a clothesline.
What about the energy you use? Can you think of any way to start using solar energy?
Maybe your family could use a clothesline, or put in a solar water heater,
Or even install a photovoltaic system.
Maybe your class can make a solar power oven.
Every step, big or small, can make a difference.
That's right, Crystal. Let's all start using the clean, renewable resource of the sun. Want a cookie? Oh, sure. That's good. Great.